Okay, so
All right, guys. So while Eric's preparing, I'll just let you guys know that today we're gonna do something called geometric construction. And basically, the idea is to create shapes and lines and points using only a compass and a straight edge. And notice how I said a straight edge and not a ruler, because in geometric construction, you are not allowed to measure. So you have to purely use a straight line and the compass to create any line or thing that the problem asks you to create. So Eric, you want to go ahead?
okay, so if y'all can see this, yeah. So can anyone? Wait, let me see.
You might want to zoom in on the notebook a bit. Okay, that works. Yeah.
Yeah. Okay. Sorry if it's a bit blurry, but basically, let's see what a compass actually does. So a compass is basically just this thing. There is a point here which can sort of dig into the paper, and then you have a sort of pencil on the other side like this. And basically what it does is if you just draw like this, it will create a circle. It's not very clear in this on the camera, but basically if you draw something like this, it will create a circle. And if you move it around, okay, then it will create a very big kind of round shape, a circle. And the definition of a circle is that every point on the circle, like, let me just trace this circle a bit. Okay, that's not a very good trace, but the definition is that if you have a center point somewhere around here, then every point on the circle will be the same distance from the center. So if we say I have O, A, B, C, then OA will equal OB, which will equal OC. So every point on the circle is the same distance from the center. And that's basically the idea of a compass. It can just create circles of any sides, and you can also, if you have, say, a point here like that, let's call that D, then you can also create a circle that has a radius of OD. And that's basically the idea behind what a compass can do. You can create all of these circles and you can determine what sides the circle is. So does that make sense to everyone? And obviously a straight edge, which in this case I'll just be using this kind of ruler, can produce lines of basically any length, and it will produce straight lines. So the idea behind what we're doing today is that we're going to try to create a bunch of crazy things, crazy shapes, using just a straight edge also, or like in real life that would be a ruler, and a compass.
Notice how the straight edge that Eric is using does not have any numbers on it, because
Yes.
we are not allowed to measure in geometric construction.
Yes.
All right, with that, Eric, let's begin the first construction.
Okay, so let me share my screen real quick. Okay, so instead of doing it on paper, we're actually going to be doing it online, which is going to make it much clearer. And you can basically do the same thing with circles and lines,
Yay!
stuff like that.
I love doing it online.
Okay, so let's have a look. So what we're going to start first is see how we can just draw these lines and circles to create an equilateral triangle. So does anyone know what an equilateral triangle is actually defined as?
It's equilateral. Equilat.
It's defined like a square. It's a
Well,
triangle.
sort of. An equilateral triangle is a triangle in which all the sides have the same length and all the angles have the same measure, which is 60 degrees.
Okay. So does that make sense to everyone with the definition of what an equilateral triangle is? Okay, then I'll assume yes. So does anyone want to see how they can construct an equilateral triangle? Now, Like if you try to approximate an equilateral triangle, something like this, that's actually not going to work because you can't prove that this is an actual equilateral triangle, because this is just going to be something that you sort of approximated by eye. But if we had perfect like circles and perfect lines, then there should be a way that we can use these tools to create an equilateral triangle that has exactly 60 degrees. Each side is exactly the same length. So
Also, with a lot of these constructions, yes, you would be able to draw really good pictures by just eyeballing it. However, the purpose of these constructions is to show you a way such that you can make a shape that's 100% scientifically accurate shapes, which is why we're not going to handball them. Which is why we're not going to eyeball them in this meeting.
Can I try? I think I know how to make a triangle. I made a pentagon before. I
okay,
made a
so
perfect pentagon before.
okay, so do you want to see what, like, just put a circle somewhere? Do you want to try doing something like that?
Put a circle anywhere, any big,
Okay.
and then put lines from the very top to the side.
Like which side? Is it going to
The left side. Wait a minute. Here.
Here? Okay.
Yeah. The other line starting from the same area. Going here.
Here?
Yeah.
Okay.
And then one arrow in the middle.
Just like this?
Yeah. Oh, that's kind of a little different.
But how about we have a look? So are you saying that this saying that these are all, this is an equilateral triangle, CDG?
Not really.
Yeah, it doesn't really seem to be an equilateral triangle. And a lot of times it's just like, because like you're still kind of eyeballing it, right? You're just like trying to draw lines here, here, here. But let's think about what properties a circle can have.
I think I know how to fix it.
Mm-hmm.
If we put the D, F, G, B, that line.
B, F, G, D.
That line that has all of them.
Mm-hmm.
Put it down till it touches the base of the circle. Like what I mean by base is like right here.
So you extend a line from where?
From here to here.
Okay.
No, what I mean is like, so there's gonna be a line right here. There's gonna be two lines, then it kind of more looks like it.
So something like this, right?
Yeah.
Okay.
That's still a little weird.
Yeah. A big reason why it is kind of weird is because like when you were drawing lines, these lines were kind of like dare I say arbitrary. Because, for example, this line right here, this line, is not really like, if you were to tell someone else how to draw an equilateral triangle, and you just say like draw it somewhere here, then they wouldn't be able to follow it exactly, right? So the idea behind this is to be able to communicate this idea, how we can tell someone else how we can draw this exact shape with an equilateral, with a ruler and a compass or a straight edge. So why don't we think about like an objective view of a circle? Like what kind of thing on a circle must be the same no matter what, no matter how you draw it?
The diameter.
Yes, the diameter. So Kimmy, do you want to tell everyone else about like what a diameter actually is?
Diameter is like the point from the very middle of the circle to one side of the circle. The distance in here is the exact same if you do it anywhere else.
Okay. Yeah, that's actually really close. But a diameter, a radius, which is what you were describing, is the distance from the center point.
The diameter is the both, like from side to
Okay.
side, right?
Yeah. Okay. Now you're
That's
right.
correct. It's 2 times the radius.
Yeah. So you put one here, and then you put another one to the other side. But we can easily just use this sort of line function to extend BA and make it the diameter. So now CB is the diameter of the circle.
Oh, now I get it.
So also remember, you can draw as many circles as you want. So do you want to see how, after seeing this diameter, we could draw?
Well, I can make a basketball. That's what.
Huh?
I can make that a basketball.
Yeah, that would.
Do right here, and then it become a basketball. Nothing else. I don't know how to draw an equilateral triangle now.
I'm gonna give
So-
you a hint. All right, maybe see if you can add another circle that would give you the third point of the triangle. Because right now we have 2 points, A and B, that seem like really good points to start with. So if we can just locate where the third point should be, we would have the triangle, right?
Oh, I get it. How about we draw another triangle starting at the very top, like very straight top of the circle?
Well, actually, how would you figure out what the very top of the circle is with a ruler and a compass?
A ruler?
Yeah,
How
with
about we
a
just
straight
switch the line over? That'll cause it to be on the.
But the thing is that, like, using these tools, if I want to try to draw exactly to the top,
It's hard.
I don't really know where exactly it is. And remember, like, when in the beginning we talked about how we were trying to do it precisely. All this stuff has to be precise, and every time you do it, it has to yield basically the same shape. Okay, but how about we think about this? An equilateral triangle has three equal sides. But if we draw, say, just a random line here, what can we say about DAB on the definition of a circle?
Go down.
The triangle DAB, this triangle right here.
It is almost
Say
one
something, we
fourth.
couldn't quite hear you if you would like to repeat it.
Sorry, talking to me or?
No, Jack, I think Jack
Okay.
was trying to say something.
Oh, okay.
All right, I guess Eric, you should continue.
Okay, so if we remember, any point on a circle, doesn't matter where it is, whoops, I just drew some lines, but it will be the same distance from the center. And we know that A is actually the center of.
Oh, I get it now.
Yeah, and because of that, what is the relation between DA and BA?
They're the same distance.
Yeah, they're the same. DA, the length of DA equals the length of BA. But the problem is, of course, that we have this other length, DB, which we don't know that length, and we can't find a way to make sure that DB equals DA and AB, right? We don't know. But what if, because think about it, D could be anywhere on the circle, but what if we create another circle like this? Now we can find a point on this circle where every point on this circle is the same distance from B. But if we remember, a compass can actually draw to any other point with a radius that is the same length as AB. So this circle is the exact same size as this circle, as the circle.
Which means then we can find the length of the other one.
So the length of the other one is actually the same because we are basically putting the kind of sharp point
it
of our
has to
compass on
be.
B.
So it has to be. So the thing has to be this long, cause it has to be this long, cause that's the diameter I mean, that's the radius of the circle. And that means this angle right here is over. It's an obtuse, right?
Well,
No, it's still an acute. It's just
yeah,
over 60
but
degrees.
we don't actually have to think about acute angles. We can actually just think about length. Because if you remember, every point on this circle centered on B, this new circle that I just drew, is also the same distance from B. And A is also the same distance from B. So BA equals BE, which equals BF, and so on.
That means
That,
this
does that
shape
make sense?
should be the triangle.
Which shape?
This shape that I drew.
So basically, what Kimmy is saying is that, actually, let me just get rid of these. What Kimmy is saying is that if we create a point here on the intersection of these two circles, that means that BE is the same as BA. But we also know that BA is the same as AE, right? Because these circles are the exact same size. Then if we create this triangle right here, we can easily see that EA equals AB, which equals BE. So does that make sense to everyone?
This is an equilateral triangle, right?
Yes. So EAB is an equilateral triangle.
A mathematically perfect equilateral triangle, meaning that every side is exactly the same. Like they're identical and there is no rounding involved.
Yes.
Is there any way we can prove that?
So
Because like Geo, does it have like something like a ruler that we can like measure to make sure?
yeah, we could. I'm sure we probably can. Let me see. So I think we can.
Rick is finding that ruler, Kimmy. We can actually prove it using geometry because notice how E and A are points on the circle centered at B, right? And that means BE and BA are the same length. And here, let me, Eric, I think you're shifting your screen. Okay.
Oh, sorry about that.
So BE and BA are the same length. And now when you look at circle A, E and B are points on circle A, which means AE and AB are the same length. And so we just proved that the three sides of the triangle are completely equal, which means that they're by definition equilateral. Does that proof make sense to everyone? Does anyone have any questions? All right. So Eric, I think Kimmy was asking you to measure it.
Yeah, but
All right.
obviously, like what Hamo said does make a lot of sense. But if we really want to measure it, we can use GeoGebra to measure these lengths. So there's actually a grid in the background. You can see that there's actually a grid in the background. So that's how the measures are done. But if we measure all of these according to just like this sort of grid that they have in the background that I hided, then we can actually see that EB does indeed equal BA, which does indeed equal EA. So the computer actually supports this as well, which makes sense because of the proof that Hambo and I have explained.
I get it.
So does anyone have any questions on the construction of the equilateral triangle? If not, then we're gonna actually do something based on this and we're gonna construct a perpendicular line.
Yeah. So
Very easy. Use the word, go to the word construct and find the perpendicular line.
Well,
yeah,
actually, my bad. What I really meant was we're gonna construct a perpendicular bisector, which is not only a perpendicular line, but it also bisects the line segment into two equal pieces.
So we can actually continue from like this circle, because generally speaking, when you're doing constructions, you want to start with a circle, because that is how you can, that is a sort of constant, like something that you can base your construction
AB,
off of.
you know that line AB is the segment we're starting with, and we're trying to construct the perpendicular bisector of line segment AB.
Okay, so in case a perpendicular bisector isn't clear, basically if we divide AB into two chunks, say like just putting it like putting a new point here and say AD equals DB, then if we also draw a line that's sort of perpendicular to D, then this new line would be what's called the perpendicular bisector, because it's not only perpendicular to AB, but it also splits AB in half. Hence why it's called bisector. It's like, you know, it bisects that line. And what we're trying to do is find out a way to create a perpendicular bisector on AB or any other
We
line.
just created one. We just created one.
Did I? I actually didn't, because first of all, I sort of just chose a random point on here. So you don't actually know if that's exactly the bisector, and if the line that I drew, which I basically just drew something random like this, is actually exactly 90 degrees. And in fact, you can see it's not exactly 90 degrees. And even if you were to like be as precise as possible, you think you got exactly 90 degrees, you can't make sure of that with a ruler and a compass.
Unless
So
you have a super laser right here. And then like this, you can make exactly 90 degrees.
so
Well,
Kim,
there's one thing. We could put 2 points at the end of these, and then we could line them up. That would make exactly 90 degrees.
wow, that's really smart. So so what Kimmy is saying is that if we line up these 2 points, because the circles intersect twice, right? So if we line up these 2 points, E and ED, which is like these sort of points that the circle sort of touch each other on, then we can create what's a perpendicular bisector and a perpendicular. This angle is going to be perpendicular. And let's just measure it real quick just to be sure. Oops, put a point here.
That is not the middle.
Yeah, sorry about that. And if we create it, it does indeed say that it is 90 degrees. And
What?
but
What?
can we mathematically, sorry about that, can we mathematically prove that this ED is actually a perpendicular bisector of AB?
Which
Well, we
means
could
we will
draw
have to prove that first, the angle is 90 degrees, and second, AF equals FB.
Well, we could draw a square in one of the things, and then we can measure all of its lengths and all of its angles. That would prove it.
That's a very interesting idea, Kimmy.
But if we draw a square here, I know this is not a very good square. The angle would probably be 90.
But how would we draw the square, right?
That makes sense. That's good.
So we can actually think about it like this. Remember how before we drew an equilateral triangle like this?
Yeah.
You can also obviously draw another equilateral triangle over here, right?
That
So
would
we have
make
EAB,
parallelogram.
yeah, and then ABD, right? But if we look at ABE, then that means this triangle right here, this triangle right here is basically an equilateral triangle. And if you draw this line down from the top of an equilateral triangle, because like in any triangle, let's say we just draw another triangle here like that, you can always find
An
a
equilateral triangle? Because that's like an equilateral.
Oh yeah, that's not an equilateral triangle. This is just a random like dumb triangle. miscellaneous triangle that I drew. But you can always find that there's a perpendicular, sort of a perpendicular line coming down from the top, perpendicular to that. And you can also find a line that that bisects the line on the bottom, like this. So this line does not necessarily create a perpendicular. GJ is not necessarily perpendicular to HI, but but you can also find a point that's bisects HI. So we're trying to prove is that EF not only creates a 90-degree angle, but also creates an AB. So what we're trying to find is that AB, the bisecting point of AB, is the same as the sort of coming down perpendicular point on AB.
Students, a hint, I'm gonna quickly mark the sides that are equal.
Those sides are equal.
Yeah, those sides are indeed equal, right?
The middle
Because of
four
the
sides are
definition
not
of a
equal.
circle.
Because remember, the two circles we drew are of equal radii. And by the way, radii is the plural for radius. So if they have the same radius, then the radii must be the same length, right?
Oh yeah. Now this looks complicated.
Well, to
Yes.
give everyone another hint, I'm gonna highlight this triangle right here and this triangle right here.
I don't know how to highlight a triangle.
It's fine, Kevin. You don't have to highlight it. But the point is, guys, try to think about the triangle AED and DBE. Like, do these triangles look equal to you? Do they look congruent?
Well, why not? Duh.
Well, Kimmy, in general, in mathematics, the question isn't why not, but why yes, isn't it?
Well, yes, it is.
Okay, I think everyone seems a little stuck, so I'm gonna just give the proof here. Hey, Kimmy, do you mind removing your annotations real quick?
Okay.
All right, thanks. So as I was saying, AE, AD, BD, and EB are all equal sides. And so by SSS congruency, we know that AED, which is this left slender triangle on the left, and EBD are congruent triangles. And in geometry, congruency just means that they're exactly the same. And SSS congruency is basically stating that if two triangles, their side lengths are completely equal, for example, here, AE equals AEB, AD equals BD, and ED equals ED. So all three sides are completely equal. So we can deduce that the three triangles are completely congruent. We're not
Can
going
you
to
measure
prove the SSS congruence theorem because it's more of a understanding. It's an axiom, which means you're taking it for granted. You can't exactly prove it. But anyways, as I was saying, these two triangles are congruent, which means that these two angles that I'm labeling here are equal as well.
Can we like try them?
This is why I just said makes sense to everyone. We proved that AED and DEB are equal congruent triangles. So we know that the corresponding angles AEF and FEB, which are the angles I draw here, they're completely equal in terms of measure. Does that make sense to everyone? Does anyone have any questions? All right, if you have any questions, feel free to ask it in the chat. But continuing with the proof, we now see that AE is equal to EB. We see that EF is equal to itself EF. So by SAS congruency, I'm going to write it because all these congruency theorems might be a bit confusing. SAS congruency allows us to deduce that these two triangles are congruent. And SAS is another congruency theorem saying that if two sides are equal and the angle between them are equal, then the two triangles are the same.
I know there's an isosceles triangle. Where
Right.
two sides are the same, but one side is different.
Oh, I mean, actually, like what I meant by two sides are equal is if we have two triangles, I know this is very sloppy triangles, but if this side, sorry, if these two sides, like these two pair of sides, I would say, are equal, like notice how this is equal to this side is equal to this side, and the angle between them are equal, then the two triangles are congruent. Does that make sense? Is it confusing the way I explain it? All right, so as I was saying with the SAS congruency theorem, we can deduce that AEF and FEB are congruent triangles, which means that AF is equal to FB. So it is a bisector of the line. And moreover, the angle is a right angle because AFE is equal to EFB. So they split a straight angle, which means each one of them is a 90-degree angle, a right angle. And therefore we have proved that ED is indeed the perpendicular bisector of line AB. Does that make sense to everyone? Are there any questions? Are there any uncertainties, questions, comments? Wait, I'm sorry, Kim, I didn't quite catch that. What was it?
Nothing.
All right. Well, since we have no questions, why don't we, Eric, why don't we go on to the next construction?
Okay. So, Hamo, can you erase your annotations?
Oh, yeah, of course.
Okay, so next what we're going to do is try to create a square. So if you remember before, we know that a square, we know how to create perpendicular angles, like 90-degree angles. And we also know how to create equilateral triangles, which is a shape that has every side with the same length. So now we're going to combine these two ideas together to form a square, a shape with every side that has a length, but also every angle is 90 degrees.
I think that's very easy.
So why don't we try that out actually? Let's just start with the circle and the diameter because that's generally where we start with these kinds of things. So I'll give you a moment to think about it.
I think I know what to do.
Okay.
Draw the circle the exact same way on the other side.
So
what I mean is like here's the point and the circle is like this.
So like
very
this.
Bad circle.
Yep.
Yes. And then what I'm trying to do is I'm trying to make it like this, like achieve it, because we already have 2 points. So then add another point, like right over here. And add in a circle.
That's also like this?
Yeah. And then I think make a line in the very middle. Make a line in the very middle. And then to the side,
Which side?
Like, since I drew these two circles, because now you know exactly where the center is. Like, the very straight. Because the two circles stop at the center. That means we know where the exact line is.
Okay.
Like, right there, we draw the exact line.
But how would I do this exactly? I
Because,
don't.
like, you know that there's two circles right here. Which means the center will be exactly between both circles.
But how would I make sure that, because it's not like these circles are like rolling pins rolling around. How would I make sure that when I'm drawing with my pencil and my straight edge, that I will for sure make sure that this is right in between the circles?
Another way. Uh, I have no idea.
Yeah, so if we look at like this kind of thing, we basically, generally speaking, when we're making lines, we connect points with points. We don't like sort of connect points with just like random edges, right? So in this case, we actually can't use these kinds of circles to draw our square, because we can use this kind of circle to form equilateral triangles, but it doesn't form any right angles unless we do something like this, but that does not help us form a square. So why don't we look at...
does actually.
Hmm?
That actually does, I think.
Okay, yeah, we can have a look at that.
Do the perpendicular thing again.
Okay.
And we could do this, go up to the side. No.
From where exactly do I connect though? Because I don't really know what exact point you're talking about.
Never mind, I don't know.
Okay. So
it's still the same problem, not getting the points exactly.
Yeah, exactly. But why don't, instead of thinking about these circles here, what other circle can we draw with like absolute certainty as to what's going to happen? What other kinds of circles can we draw? Well, of course, we can also just draw a random circle like this, but that actually does prove useful for a lot of things. But we can also find other circles to draw, and then we can create perpendicular angles.
Now what? Well, we ran out of tools. Oh.
Chemistry and mathematics,
So
a lot of problems can be solved by trying to solve a simpler problem and applying the approach used on the simpler problem on the harder
exactly
problem.
what I thought. We might
So why don't we go back to the construction we used for the equilateral triangle? Maybe there's something there we could use.
I wish we could just copy and paste it back on.
And Eric, why don't you add the perpendicular bisector as well?
Oh, okay, I see what you mean now. So if we mark a point here, then how else? Because if we think about it, a square actually has two kind of a square actually has two different like perpendicular angles, two kinds of perpendicular angles in it. Because if we draw, say, like I'll just draw a pretty crappy square here. If we draw a square here, then we know that the angles on the side are also 90 degrees, but we also know something else, which is that if we connect the diagonals like this, all of the
diagonals
angles here,
are the same side.
Yeah, they are in fact the same sides, but we can also say something about the point of intersection. We can realize that basically this angle right here, h, if we call this middle one k, hki is the same as jki, same as gkj, and which is the same as gkh. And they're all 90 degrees. So this is a pretty bad shape It's a pretty bad square, but because it's not possible to just draw a square like using these tools right straight away. But
you
use
could
that fact of a square in this problem, actually. So you want to think about this?
I might have already found a square-ish thing.
Yeah, so what you have right here is called a rhombus.
Yeah, I'm trying to make like, a rhombus is kind of like a square, just a little sideways and a little cracked up. So I think
Okay.
a rhombus might help us get a square.
So Campbell actually said that we can draw another circle to find the solution as a hint. So why don't we have a look at which other circles we can actually draw right now? So a circle,
We
basically,
could
to
draw
draw a
it on the
circle,
top,
mhm,
like right here. Could
like
draw
this.
it over there. Yeah.
And which point do you want it to attach to?
Probably
A,
this point.
F? Okay.
Yeah. Like that's the main point we're using.
Mm-hmm.
And then the same thing over here. Attached to F point.
Mm-hmm.
And then
The two circles you drew are very interesting, but I don't really think they will
oh,
help
I
us
know
draw a
what to do
square.
now. I know what to do now. I
Uh-huh.
got it. So a circle right here.
Circle starting
Going
from
to
this point,
B.
going to B.
A circle over here. Going to A.
It's like the Audi logo.
Now right here. A point right here. Like a line right here. From here.
Here?
Here. No, a line.
Oh, a line from there to here. Okay.
Draw it so good that it disappears.
Okay.
And then right to here. And then to here. And then to the other side. No.
Well, it's actually
Never
really cool
mind.
because you have actually discovered another way of creating equilateral triangles. Because if you notice, DEC is actually an equilateral triangle as well.
Oh.
And we can prove that, but for now we'll go back. But this is actually this is actually quite brilliant. You can also see another way to create equilateral triangles.
And
But
in fact, it's an equilateral triangle that's inscribed in a circle.
yeah, so we will probably talk about inscribed shapes in the future, where shapes, each corner of the shape is on the circle. But let's I digress. And I think we should also go back to that kind of idea of a square and its diagonals, because if you notice that, okay, let's just pretend this is a square, it's a very trash square. But if you notice that if this is a square and you have a point in the middle like this, then all of like okay, so like J to K is the same as I to K, which is the same as K to H, which is the same as K to G, just like how the angles are all 90 degrees. And if we remember, what is the definition of a circle? Well, the definition of a circle is where all of the points is a set of all of the points where the circle, like, which are the same distance from the center K, a certain distance. Which means that,
That
in
means
theory,
you could draw an X in the very middle, or do it like that. And you could either draw an X in the middle of a circle and then surround it, or we could draw a circle in the middle of an X and then surround it. I don't understand what I'm talking
Well,
about.
guys, we really just have to draw one more circle to finish the problem. And Kimmy has been doing a great job carrying today's conversation, but I really want to hear from somebody else. Uh, Joyce, Wei, WT, Lloyd, do you guys want to try and guess at which circle we should draw to finish the problem? Just take a wild guess. Joyce, Lloyd.
I have no
here-
idea. So calling
Okay.
me is basically
So-
useless.
Yeah, so let's go back to what I just said about the square. So if we remember how K, all of these points are the same distance from this sort of diagonal center, that means that we can actually draw a circle centered on K that goes to all of the outside points. Now this is a very bad square. It's not an actual square, so it doesn't fit exactly. But if we had an actual square, then all of these points would be on the circle that I centered at K. And what that means is that if we have two perpendicular lines like this, something like this, two perpendicular lines, then we can actually draw a circle centered from this middle point. And if we draw a point here, R, S, and then we draw some other points here, all of these other points will also be the same distance from P if we draw this circle. And if we connect all these points, because of the property I just talked about, these points actually form a square. So I'm not sure if this makes complete sense to all of you yet, but if you have any questions, you should ask, or if anything's unclear. So does that make sense where you can draw a circle through centered on like the hitting at perpendicular line? So Wei says that you can draw a circle centered on F. And does anyone want to see where the circle can actually lead to? Like where can we connect the circle? We can connect
I would
it
say
here.
anywhere.
We can connect it here, and we can connect it all the way over here.
I would just say somewhere small.
Let's let Wei finish the observation. Wei, where do you want the circle to stop at? As in, how big do you want the circle to be? Because it's fine, Wei. Just go ahead and type in the chat. Like, tell us where's the second point that you want the circle to stop at. Like, how big do you want the radius to be? Because the circle centered at F is a great idea, but any place probably wouldn't work.
Actually, I would say it can, because as we just discussed, you can put any circle, and
Yes.
if you put a circle even here, then you can connect all of these points, because we can find all of these points on like this, and you can connect all of these points. You can put a circle basically anywhere. Whoops. Okay, so let me just
Try to erase the V.
Yeah, erase
This
V.
is what's annoying about having 99 squares, 99 circles.
Oh, there we go. So if we put points on all of these areas and we just connect them, as discussed before, this is guaranteed to be a square because it has diagonals that are perpendicular to each other, because we have already proved that. And also WF equals FV, which equals FA, which equals FZ. And what that means is that, also FA is FA1, because there's too many points right now. But basically, that means that we have defined all these properties of a square, and we know that these 4 points fit those properties. They're all the same distance from their diagonals, like intersection point, and the intersection point has 4 90-degree angles on it.
This is amazing. We made a cheese it.
Yes.
We made a huge cheese it.
But personally, I think the best way to do it is just to do it like this.
Because
it
it
just, like,
looks nicer.
it just removes the mess. So like, it just removes the mess and it makes it a lot clearer what's going on because there's not as many like lines everywhere. So something like this is very
It's
clear.
a tiny cheese.
Yeah.
We can measure the size and we can see that all of them are like exactly 90 degrees, right?
Yeah, we can see that. Let's go through it. 90 degrees. 90 degrees. 90 degrees. Oh shoot, that's 91. I think I probably clicked in the wrong spot. Okay.
Told
But-
you one
Probably
of
because
them
the B
has
is like
green
it's
in
not quite on that thing, but
Yeah, the B is not quite on it. Okay, but generally speaking, yeah, it should be 90 degrees if I am proficient at clicking. So yeah, so I think this is actually a really cool way of constructing a square.
it. Geometry dash.
Geometry dash. Yes, we have just dashed through geometry. But yeah,
And
that
now
was
what
actually quite a hard problem. But let's go back to something that Kimmy discussed before, which was this kind of shape with a bunch of just lines like this, connecting them. And
And then I have two more on the top.
yeah,
I think.
so
No, I did not. No, I didn't.
Hambo
Yeah, I
actually
had
gave
two
us
more on
all.
the top.
Mhm. So Hambo actually gave us a little spoiler in the chat, his extremely useful messages. He has said that we can actually use this sort of thing to construct a hexagon. And does anyone want to see how we can construct a hexagon using these 3 circles?
Me. I want to see everything we can create. We created a big cheese-it. Now we're gonna create a 5-sided cheese-it.
hey everyone, we just have to click 6 points and we get a hexagon. Does anyone else besides Kimmy, because Kimmy has talked way too much in this meeting. Kimmy, good job. Does anyone else besides Kimmy want to point out what the 6 points are so that we can connect them and form a hexagon?
I
I'll
have
give
no
you
idea where the 6
one.
points are.
Yep, in fact, Neil already gave us the points. Good job, Neil.
So let's just draw these points.
Oh, I
Yes,
see. And then
Neo
the last
is
two are on the side.
Yeah, Neo is the one. Okay, so we have
And we
this
need
sort of,
a 6-sided cheese-it.
well, you can say a circle is technically an infinitely sided cheese-it. I mean, if that's what you consider a circle, it depends on the definition of a circle, but that's not the point of today's meeting. Anyway, so for this hexagon, how can we actually prove that this is a hexagon? I mean, we can look at it, it seems very hexagon-y or hexagonal, but how do we know for sure that this kind of thing with these compasses or compi or okay, whatever, can form a
Measure
hexagon?
it.
Now we can measure it, which is what we can do to confirm, but without measuring it, how would we know? Because like we're assuming that we only have a compass, a ruler, and a pencil. So how would we actually know that this is a
I know because it looks hexagon-y.
well, it looks hexagon-y, but is it really a hexagon? This looks rectangular, but it's not necessarily a rectangle, right? It looks about right, but how do I know that this is a hexagon? Now remember, a hexagon is also formed out of 6 equilateral triangles, right? These 6 equilateral triangles will fit together to form a big hexagon. And this hexagon has equal sides, DE equals EB, which equals BF, which equals GF, FG, which equals GC. All these sides are equal. But remember how it's formed out of equilateral triangles? We also know that in a hexagon, all of the points in the center are also the same length as the points on the side. So we know that DC equals CA, which equals DA, right? So because of this property that hexagons are made out of 6 equilateral triangles, we can actually use this to our advantage. And does anyone want to see how they can prove that this hexagon is indeed a regular hexagon? Because regular hexagon basically means that it's like the most stereotypical hexagon with all sides being equal. So does anyone want to see how they can prove this?
I have no clue.
Well, let me actually just highlight this hexagon real quick, just to make it a bit clearer. Okay, yeah, that looks pretty cool. But remember, a hexagon is actually made out of these 6 equilateral triangles. And also, we can remember that basically what we need to prove, we already know that DC equals CG, right? Because these are all equilateral triangles. Like we we proved this before. We've made equilateral triangles using 2 circles. We already know that DAC is going to be an equilateral triangle. We already know that CAG is going to be an equilateral triangle. And because of that, we know that DC equals CG, because all of these sides, all of these lengths are the same. And similarly, we know that EB equals BF. And we know that these lengths are the same because of circles and stuff.
Then it means the middles have no choice but to be the same.
Sorry, can you repeat that?
The middles have no choice but to be the same.
Why?
Because the outsides are the same, so the middle, there is no possibility of it being wrong.
So, what do you mean by that?
I mean, like, we know, the 4 triangles surrounding the 2 triangles. Wait, I'll show you. This triangle, this triangle, this triangle, and this triangle are the same, right?
Mm-hmm.
This triangle and this triangle we don't know.
Yep.
But even though, since these 2 are the same, there's no possibility of those 2 to be incorrect.
But like, why, right? Well, I don't.
Because like they already took up the equal amount of space. If they don't, they could not sure. Okay, I get it.
But
I
we
get it.
need to prove this, right?
Yeah.
Prove this like logically.
Direction, but we need a bit more details, Kimmy.
Yeah. So Hambo has actually drawn the angles. If you remember in the beginning, we talked about how equilateral triangles are actually 60-degree angles, have 60-degree angles. And what this means is that, and remember, like DA also equals AE, right? And we just need to know that either DE equals all of these other guys, or that DAE is a 60-degree angle. So we just need to know that, let's see, this forms a 60-degree angle. And how can we prove that? And Hambo's sort of nice hint right here is a great way of seeing this.
Well, we could ask a math genius to come.
Math genius?
You could call the president and make him come over here and see if the
Unfortunately, the president is not
Probably at
available.
this meeting right now.
Well, then just grab a ruler or something like a tractor beam.
But we don't have that. We don't have these kinds of measurement devices. We can only prove it using what we already have.
Hey, I see someone gave us the answer in the chat. Wei just pointed out that 180 minus 60 minus 60 equals 60.
Mm-hmm. So what he's saying is that
Half a circle is actually 60 times 3.
yeah, so CAB, this right here, let's just draw that real quick. Like from here to here is actually going to be 180 degrees, right? Because 180 degrees is basically just a line. It's just flat. And if we draw these points on top, we see that there's 60 degrees here, 60 degrees here, which means that the only amount that we have left, 180 minus 60 minus 60, is going to be 60 degrees. And because of that, we know that DAE is going to be 60 degrees. Thus, we have proved that DAE is an equilateral triangle. And similarly, we can also prove that GFA is also an equilateral triangle. And thus, we know that we have a big hexagon here, formed by these two circles. And now it's actually really great because now you can construct so many different shapes, so many different things using just very basic tools, a ruler and a compass.
That is just weird.
Hopefully,
I never thought a ruler would actually mix a ruler and a compass would make so much stuff.
Yeah.
Yes, hopefully you guys found what we just talked about in the past 1 hour very interesting. And I always think that geometric construction is cool because you can flex on your friends about like constructing cool shapes with just the ruler and the compass. While they have to use a protractor to draw a hexagon, you can just draw it in a matter of seconds, which is why I think it's pretty cool.
It's a cheese-it with holes in it.
And it's all made possible by just the power of circles. Like, circles are honestly just such a great tool in geometry in general.
Circles, you can never actually draw them wrong if you have one of those.
Yeah, compass.
Yeah, unless they're bad at using it.
Yeah. Which I am actually kind of bad, but yeah.
I'm worse. I can't even draw a full circle.
But overall, I think this was actually a very fun thing, wouldn't you agree? A very fun activity that we did today.
Especially when it was a cheese-it.
Yeah.
Guys, that's all we have to talk to you about today. And if you do not have any other questions, thank you very much for coming to the meeting, and hopefully we'll see you next week.
Wait, look, there's actually a huge equilateral triangle in there.
Where?
Look, that's an equilateral triangle.
It is, yeah.
So, and there's a kind of like a mini square, a mini rectangle to be exact.
Yeah, that is indeed a rectangle. Yeah, so you guys are the meeting is over, but we do have another proof if you want to stay around and just see, but you're not required to.
People are leaving, so I guess we'll just show another proof. We'll show the other proof for the hexagon.
All right, we'll show another proof. Okay.
I mean the other construction. Let's show the other construction first.
Okay. Let me just clear all this stuff.
Let's draw a nonagon.
A nonagon? Oh, that is much harder.
I know, because there's so many sides.
Yeah, and because a lot of it is also because it's just very uneven, right? For like a square, you have all 90-degree angles, which is pretty like simple, right? Triangles, you have 60-degree angles. All this stuff.
Pentagon, I think it's so far the hardest.
Yeah,
I started drawing a pentagon and it took me 2 hours.
Yeah, okay. So, but let's just have a look at another hexagon. So I'll just draw this right now. It's a much more pretty, I guess, much nicer like looking way to create a hexagon. Whoops. Okay. If you just draw a hexagon like this is actually what OPS, the Art of Problem Solving, says in their geometry book, Introduction to Geometry book. This very, very cool looking method, kind of flowery method. But yeah, so you can actually see how these points connect to form a hexagon, and
There's
it's
a
very
flower inside of it.
yeah, it's very nice looking. Generally speaking, in real life, if we were to actually do this, we don't actually need to draw the entire circle, We just need to draw like this sort of arc from D, A, B. But because we're using GeoGebra, we can't actually do that. So which is why it looks like this. But generally speaking, it would be a lot. You don't need to draw the entire circle. You just need to draw a little piece. because it'll still be the same length. CD and CB will still be the same distance.
Amazing.
Right? But because we're using GeoGebra, it's going to be like this. But yeah, so this is a very interesting other proof, another other method. And
Can we do a pentagon?
we
I feel
could
like
do
it's
a
impossible.
pentagon, but it is much harder.
I knew it.
Yeah. So Neo says that it's going to be 108 degrees, but unfortunately we do not have a protractor, so this is going to be very protracted. I don't know. Okay, I was trying to make a pun. Okay, but we won't be able to use just that 108 degrees. And also, the 108 degree is actually really interesting because you can find it just using the number of sides of a shape.
Cause like one side would be 180. This side would be
Not necessarily.
90.
Yeah.
Four sides would be 90. That means half of it. And then 6 sides would be dividing 60, and that makes sense. And then 8 sides would be 30 degrees, and then 10 sides would be 15 degrees.
Well,
The meeting is already over and people aren't leaving. This is it's very funny.
We are very appreciative of your efforts to stay around and learn more about this beautiful subject of geometry. Yes.
We're already out of stuff that we plan to talk about today, but I mean, if you guys want us to talk about anything specific, we can explain it to you. So like, if you guys have anything you really want to learn about or something.
Yeah.
Because like we're already out of plans right now. So.
Or even anything that you're curious about, such as like the 108 degrees that Neo came up with.
I don't think
11-sided gon has an angle measure of 147 and 3/11 degrees.
that's correct. I just searched it.
Eric, why don't we show everyone how Neo is getting these calculations? Because I bet not everyone knows how to calculate.
Okay, so a very easy method of doing this is actually to search it on Google. But another method of figuring this out is to just look at a triangle at first. Let's just look at a triangle. So
Eric, I think you can draw accurate polygon with that polygon function over there.
Oh yeah, you are right. Let me intro. Okay. So let's look at regular polygons, just like this.
Oh, by the way, 1 second. Wei said how to find a midpoint of a line segment. Well, Wei, it's actually very simple. You can use the exact same construction we used to construct the perpendicular bisector, and the intersection point will be the midpoint of the line segment. Does that make sense?
Yeah. So if say we actually let's just start with A and B. If we draw circles from A to B, if we draw circles like that, then we can easily find the bisector of A and B. And not only we can find the bisector, we can even find the perpendicular bisector as well. But this point where CD goes crosses AB is going to be the bisector of AB, which is actually a really interesting way of finding these kinds of things. So does anyone have any other questions? Let's see.
Cut a pie in half.
Cut a pie in half?
Well, I suppose you just draw a line through the middle, right? It's just the diameter.
I can draw a line through the middle, draw a circle, and then I can draw an incorrect line through the middle. Can't you draw an incorrect line in the middle, like right here? That, even though it's starting from the center, you can still make an incorrect line. does not connect to both sides. Then it's not a line.
It's not very clear what Wei means by cut a pie in half.
I don't know either. I'm just cutting a
Wait,
Yeah, I don't
actually,
really
there's
know.
something interesting we could cover. Eric, why don't we show them the construction for how to construct a perpendicular line to any line segment?
Okay.
Like from a given point. So
Okay.
we'll start with a line segment and a point above the line segment.
Wait, actually, do you want to try requesting control so that you can just explain this one?
Oh yeah, sure. I'll share my screen.
Okay, yeah. You should try. You should do this one.
Okay.
Some nice music, by the way.
Does everyone see this? Let me get rid of this. Yeah.
pie grid.
All right, so here we're gonna try to construct a
A
line
car.
that's perpendicular to AB going through C. All right. And for the sake of making this easier, we're gonna extend the line a bit. So, but still, we're trying to construct a line perpendicular to AB that goes through C. And so
Instead
it's
of
actually, yeah, the method is actually very similar to that of which we use to construct this perpendicular bisectors. But what you do is you draw any random circle you want as long as it intersects the line at 2 points. So I'll just make it this big. And then using the intersection points, you draw 2 more circles. And they're of the exact same radius because notice that EC and CF are
It's a
radii
watermelon.
of the same circle, so they're exactly the same length.
It's a watermelon.
And from now on, we just use the method we used to construct the perpendicular bisector. And I can't quite move this. Okay, I'll just do this smaller.
You can use
But you
the.
just connect these 2 points.
You said you only opened. You said you only made it longer just a bit. That's not a bit.
All right, but anyways, as I was saying, you use the same method they used to construct the perpendicular bisector and draw this line, and we have completed the problem as we now have a line through C that's perpendicular to AB. So it's like an extension of the construction we use for perpendicular bisectors, which is quite cool. Does anyone have any questions on that?
Someone create something a dumb question like cut the pie in half.
High enough, huh?
Yeah. Could you please explain what you mean by cut a pie in half?
Make
So-
someone bake a pie and then make them cut it in half.
So, if you do remember, we can just easily create any diameter, and that would automatically cut the circle in half. So, I guess you could cut a pie in half.
You cut the pie in. I don't know. What noise is so loud?
So, Wei says cut a slice of pizza in half.
I think that comment was in fact from earlier. Well, I mean, guys, the meeting's over, so. If you guys don't have any questions, we're gonna end the meeting.
I'm just staying.
Okay, but hey, if you guys really want to stay, why don't I just talk about how you can find the amounts, like the angles of regular polygons based on the number of sides.
Okay.
So we can first find the total angles, like if say in a triangle in a triangle, all the angles add up to 180, right? Does everyone like understand that? Does everyone know that? The angles add up to 180. So since the angles add up to 180, every time you attach another triangle on here, the total angles, that's like the adding up all the angles of this new shape A, B, D, C, is going to add another 180 degrees because you're adding another 180 degrees like B, D, C, these like another 180 degrees from this other triangle. You're not removing any angles from this other triangle.
360 degrees.
Yeah, so this total one is going to be 360 degrees. And if we just let me get rid of this line in the middle, and we can also see that every time you add a new triangle, like attach a new triangle like this, you will add one side because you will be just attaching it something like onto a side before, but then you'll also be adding a new side like this.
Now it's going up to the
adding 2 new sides while destroying one side. And thus, every time you increase the number of sides of your shape, the total angles, the sum of all of the angles will increase by 180. Thus the total angles, internal angles, which means these angles here, the total, like the sum of internal angles is always going to be the 180 times 3 plus n. If the, oh wait, no, 180 times, times 180 plus 180 times n minus 3.
Who's Joy of Rice?
Joy of Rice is Hambo. Okay.
All right, guys, we are way over time.
We are way over time, so
no one has any
we're-
questions. We're gonna end the meeting here.
All right.
Again, everyone, thank you very much for coming, and we shall see you next week.
Okay.
Bye.